Swayam Prabha, free DTH channel for education.
Hello everybody, welcome back to the online video lectures of the medical imaging course. In the last video lecture, we were discussing about filtering based methods for image enhancement in the spatial domain. More particularly, we have discussed about the definitions of correlation and convolution in 2D, and we have also discussed few enhancements that are related to image smoothing or to an extent denoising. Particularly, we have discussed about average filter, weighted average filter, and Gaussian filter. In this video lecture, we would look at few illustrations for some of these already discussed methods, and then we will continue our discussion about denoising filters, particularly the median filter. Then I would make few more points about dealing with the boundary issues, and then we would discuss about gradient filters and Laplacian filter for image enhancements in the spatial domains. Let us start the illustrations with the help of a simple smoothing filter, where this is the center of your kernel or mask, whatever you call it. So you have two on this is a mask of size 5. For illustration purposes, we are looking in just a 1D case. So at whichever pixel you want to compute this value, so there you keep this. So this basically the magnitudes are shown on the y-axis, and these are the pixel numbers on the x-axis. So you simply convolve or convolution and correlation are same in this case, as the mask is symmetric. So you could call either you convolve or correlate with this mask the image, and thereby you would be getting this weighted average mask. And the next improvement that we had looked at is giving more weight to the center pixels. Let's say this could be 6 here, weightage of 6 here, 4 to the next neighbor, and second neighbor you are giving 1. So the total sum is 16 here, so you divide it with 16. Now you apply this mask by keeping this as the center, this aligning with each of the pixel that where you would like to find out the value, and then you would get this as your result. That's weighted moving average. Instead of going for an empirical weighted average things, you could go for a special case of Gaussian filter, where you would be using minus x square plus y square by sigma square here, and one normalized with 1 by 2 pi sigma square. So if you look at now in 2D, this is how it looks like. And for example, a 3 by 3 mask is something that could look like this. Maximum value 4 here. Immediate neighbors all have the next high weight of 2 here, and diagonal elements have the next high value of 1 here. And we are doing a discretized operation, so it's not like you have it at every non-integer value. So that's where you are discretizing this. So while you are discretizing this, as we discussed in the last video lecture, the kernel size is dependent on the variance that you could observe from here. For example, this is showing you the graph when your variance is less. Let's say it is 2. Similarly here you have a larger variance here. These are essentially drawn at the kernel values, where you are varying kernel size of 30 by 30. So it is varying from 0 to 30 here and 0 to 30 here. So 30 by 30 kernel. You could see here when your variance is large, if these all values are going to be 0 as you move far away from here, right? On the other hand, you would require more values when you have, for example, a high variance compared to the earlier one, right? So this should already tell you that if your variance is more, you should have a bigger kernel for performing this Gaussian operation. I just wanted you to take a look at how it is does in MATLAB. For example, there is a function called image Gaussian filter. If you want, you could simply give the sigma value. If you don't give anything, I guess it takes 0.5, but you could specify this is what you would like to have a control over. So, okay, then if you don't further give any of these values for the kernel size, okay, that is what it is referred to as filter size here. If you don't give any value, what is the value it takes? You take twice the sigma value, take seal of that value. For example, anyway, one kernel at 0, and then here number of kernels would be whatever are there here, the number of kernels. I'm just showing it in 1D, but just for illustration, but you know that. Okay, that you take 2 times sigma on this side, and similarly here you take 2 times sigma. Okay, so and then anyway 1 for the middle one, so that's what. So essentially it takes 2 times seal of 2 times sigma plus 1. So suppose your sigma equal to 1, that means the window size would be equal to, let's consider the case of 1D. So this is 2 into 2 4, a size of 5. I think if you extend it to 2D, it would be 5 by 5. Yeah, I think this is a 2D one because it's a 2 element vector, right? This is a 2D one. Similarly, if my sigma equal to 5, what would I get? The W will be equal to this side 10 10, middle one, so 21 by 21. Anyway, you could always, if you want to play with this parameter also with different value, you could always do that by giving this name filter size and then mentioning the value. This is just the default value. So just one more point that I would like to re-emphasize is, while you are applying this filtering operation, or you can call it when you are doing correlation, or in other words doing convolution, what you need to take a look at is also what would be the size of the resulting image. Suppose when you are calling a filter in 2D, so there are 3 possibilities that are typically looked at. Let's say this is your image, you consider this F as an image. If you give full, what would happen? Let's say this is of image size n by n. Okay, I could have considered different rows and columns, but doesn't matter. And let's consider this is of size w by w. So even for when there is an overlap of even one element here, okay, so for this part also, this being the center, okay, to that also it computes assuming some padding here. That padding we will just come in the next slide. Then it gives you the image of this increased size. So what should be the overlap here? You just take a look into it. So accordingly it will give you the size of your image. So where at least there is a single pixel overlap while you are moving your Z, that would be the size. So I leave it to you as an exercise to figure out what would be then the size of the resulting image, given that your F is n by n and your G is w by w. And once you come up with an answer, you go to MATLAB, you give some F, you could just create a random matrix, and G you give the size and check if it is working or not. Okay, now when I say same, what it would do is it would do only this operation only for the pixels that are there within F. So then your output would be the same size as this one. Okay, resulting image size will be in this case n by n. Now another one is, you don't want to assume any particular values for padding or the boundaries. You just want to go ahead with whatever values are there within the image. So in that case, what you do is, here you would see, you would compute, for example, this is w by 2, assume that, okay, or seal or whatever. Then this is what you would give you as valid output. So it gives you only till that region of the image where your window is fitting within the image. So this also I would give you as an exercise. Work it out for yourself. What would be the valid size when you are given a size of n by n here, and the size of your kernel is w by w. You can also assume that your w is a odd number. So then you find out the answer, and again you check it with MATLAB code. What kind of padding needs to be used while performing this correlation or convolution, that also you could mention when you are calling an inbuilt function for performing these operations. So one thing is referred to as circular. It is particularly something you should definitely go for when you are looking at the frequency domain properties. This would something that retains those properties. So it is like you keep the same copy on all sides of your image. So that's what circular thing. Then replicate is pad by repeating the border elements of the array. So in your image, whichever is this column of intensities that simply gets repeated to any number of columns here. So that's what is replicate. So for example, if your image is already having 0 values and a large border, and there is no intensity issues at the borders for significantly enough number of columns and also rows, then something you could simply go for replicate. And another thing is symmetric, okay, where you do a mirror reflection around this edge. So this first column would become the first column here. Suppose you have a column here, that would come as the second column here that you are padding, okay, and then you have the third column here, that's what would come here while you are padding. So before calling this correlation or convolution filters, you need to figure out which is the appropriate type of padding for your particular image and your particular operation. So with that, we will come to one more type of denoising, which is based on statistics based denoising. In most of the cases that we considered earlier, the inherent assumption is that your image is having a Gaussian noise added to it, but that's not the only noise you would encounter. For example, if you are having a salt and pepper noise, I'm sure all of you know what it means by salt and pepper. So usually if you consider an 8-bit integer, salt is white, so this is 255, pepper is black, 0. So in your image, only randomly these values of 0 and 255 are getting added, assume that. So that's why it's referred to as salt and pepper noise. Okay, if these are the values that are getting added to your image, most of the times nonlinear filters, particularly filter like a median filter, would be able to do a very good job even when compared to your weighted averaging filter or Gaussian filter. Let's see some illustrations for it. First, before that, let's see how a median filter works. Suppose you want to figure out what should be the new intensity value that you would like to assign for this pixel, okay, then consider a 3x3 window around it. Then all the values whichever are there, intensities in this 3x3 window, you order them either in ascending order or descending order. Then you take the middle of that value, and then in the output image you replace the earlier intensity value with this one. This is very good at removing spikes, particularly it removes spikes coming from addition of salt and pepper noise, okay. And now, although I mentioned that this is a non-linear filter, think about it, why is it non-linear? Okay, that's what I leave that question to you. How can you say that median filter is a non-linear filter? For the time being, assume that this is a non-linear filter. As this is a non-linear filter, you won't be able to use convolution and correlation as such with the mask for finding out this median filter. Let's analyze here few more properties of this median filter. So from here you could already expect that your image is something which perhaps is like this, right? And then there is a sudden discontinuity happening here, and you have another set of intensities here, and then this is another set of intensities that are going. Assume that this is just we are looking at one row of your image, okay. So from here you could expect that since there is a variation only here at one point, this is perhaps got introduced because of noise. Now look at what would happen if you are applying a median filter versus a simple mean filter. A median filter, when you are here, you take, let's say, 3x3 window, you order them in the descending order, so one of these two values would be picked up, so this would become again same as this, isn't it? And then there is a sudden edge happening here, right? There is a sudden transition or discontinuity happening here that got nicely retained here while you are using the median filter. Because what would happen here, suppose I want to apply what should be the new value here. Assume a simple 3x3 window. So this is the value, let's call this as I0, and this value be I1. So what would be the values for this one? I0, I0, I1. Okay, you order them in the ascending or descending order, it would be still I0. Similarly, look at here. When you are looking at here, the values would be I1, I1, I0. So this would remain as I1. And this is how you would nicely get the profile of it. On the contrary, if you are going to apply a mean filter, one outlier intensity value is going to bring a change throughout all these values and also at all these points. This also the profile it is going to modify. This you could take a simple example and work it out for yourself. So what's the conclusion that we could draw here? When you have salt and pepper noise, usually median filter is much better than mean filter. Okay. Second point, it is very good at preserving the edges. That's the second important point. Third point here, median filter, when it is applied on a given input image, it does not introduce new intensity values in the output image. On the other hand, any of the mean filters or weighted averaging filters would introduce new intensity values into the image. As you could see here, see, median filter, it is only ordering them and picking one of the values among them and not doing any averaging. So it doesn't as such introduce any new intensity values. But of course, median filter is a non-linear filter, whereas mean filter is a linear filter. Hope it is clear about median filter as well. Another example here where there is a image of a PCB probably which got corrupted with salt and pepper noise. If you are doing an averaging of it, this is the nature of the image that you would be getting. On the other hand, if you are using 3x3 median filter, you will get a very good image, as you could see here. So again, this doesn't mean that you always go for median filter. It also depends on what kind of noise your image got corrupted. Okay, the nature of noise you have is salt and pepper noise, then median filter usually works better than the averaging filter or weighted averaging filter. Right, so with that we have so far seen about smoothing filters or image denoising filters that are going to enhance the quality of your input images. Other ways of enhancement of the image is by looking into the gradients of the image, because that's something that tells you about the edges. You want to enhance the edges, okay, then something you would be looking at is image gradients. Similarly, another way of improving the edge information is also using Laplacian. So those are the two concepts that we are going to take a look at. I'm sure you all know the difference between a derivative and a gradient, right? Suppose if I am taking the derivative with respect to x for an image is a function of two variables x and y, right? If I am taking with respect to x the derivative and then take this f is a function of two variables, so that's why I'm using the notation of partial derivatives here. So the vector containing dou f by dou x and dou f by dou y is what you refer to as gradient. And of course, if you have a 3D image, in case of medical images, then you could have a 3D gradient. You will simply add one more term there to your vector, dou f by dou x, dou f by dou y, and dou f by dou z. Your function f is now no more f of x comma y, but is rather f of x comma y comma z. Now, what would be the nature of these gradients? Let's say you consider a vertical edge. Okay, then if you are at this point, if you are going to compute the vertical derivative, okay, that means dou f by dou y. As you move on in the y direction, there is no change in the intensity, so that's why this would be equal to 0. All you have there is dou f by dou x. So in your gradient, the way you could interpret a gradient when you have only the x component of it is that you have a vertical edge. By the same logic, you could say here when you have a horizontal edge, by the way, this would be now perpendicular. The gradient would be, as you could see here, will be perpendicular, always perpendicular to the edge here, the direction. Okay, now you consider a horizontal edge here. Now if you are moving horizontally, there is no variation in the intensity, dou f by dou x, if you compute it. So that's why it would be 0, and only when you are perpendicular to it in the vertical direction, then there is a change that is represented. The strength or the rate at which it is changing is given by dou f by dou y. In other words, when you have a 2D image, and if your gradient has only the second component of it, then it means it's a horizontal edge, and the magnitude will tell you the rate at which the intensities are changing. Now you could have edges in different directions. Say for example, if you could see here, this is how, as you are moving in this manner diagonally, the intensity is varying. Okay, so in that case you will have both this component, right, which is dou f by, this is your, by the way, this is your x. Okay, so dou f by dou x you have, similarly dou f by dou y also you have it. So when you have both non-zero components, that means you have an edge in a different direction. This strength of this edge you could get by taking the norm of this gradient, which is dou f by dou x whole square plus dou f by dou y whole square and under square root. That would give you the magnitude or strength of the gradient, and the orientation is obtained by, this is a vectors here. So both the, for example, if this could be very high, okay, the length is telling you, assume that this is small, okay, then this would be your direction. So obviously this would be given by, this is your dou f by dou x. Okay, I am just assuming here this is your direction of y. I could have taken the other way around also, doesn't matter. Dou f by dou y. So theta equal to this, tan theta equal to vertical by horizontal, so that would give you theta is equal to tan inverse of dou f by dou y by dou f by dou x. So this is how I could compute the gradient of a given image. So for example, an image is given to me, I compute the gradient and assume that I am putting a threshold on this gradient value and making all values below the threshold of this magnitude to be 0. Then all I would be left with is those pixels that have very high gradient. So essentially the gradient would be very high wherever you have a sudden transition of intensities. In other words, wherever you have an edge. So that's how you could figure out the edges. And if you are now somehow performing a particular operation on these edges, enhancing them, and then you are adding it to the original image in some way, then obviously you would get an image which is edge enhanced image. You are anyway going to see some illustrations in this presentation as we move on. So essentially it requires computing derivatives in the x, y, and of course in a 3D image z. So how do you compute that? F is a function of x and y for a 2D case. You want to compute it with the derivative with respect to x. So you change this x value. You have this function f of xy computed at two values, x plus epsilon and x. Subtract the function computed at x plus epsilon comma y minus function computed at x comma y. So this is a standard definition of what a derivative is, isn't it? So then you take difference of these values, which is x plus epsilon minus x would give you epsilon. So this is how in a continuous case you could compute the derivative in the x direction. Now this being a discrete data in case of an image, this epsilon would be in fact equal to 1, isn't it? So then f of x plus 1 comma y minus f of x comma y divided by 1. So this is what would give me the derivative in the x direction. Of course this is not the only way I could do. For example, I could have taken also f of x comma y minus f of x minus 1 comma y divided by x minus of x minus 1. This is again 1, right? So this also would give me the derivative. Again, this is not the only way. I could have also taken f of x plus 1 comma y minus f of x minus 1 comma y divided by x plus 1 minus of x minus 1, so which is equal to 2. So that's equal to 1 by 2 into f of x plus 1 comma y minus f of x minus 1 comma y. These are all different approximations. I'm sure you have studied it in one of your mathematics courses. This is how you compute the derivative. Now this is a linear operation, you all know it. You could now perform this using a mask. So for example, if you are going by this definition, so what do you have then? You have a mask of so assume that this is my position of x, this is x plus 1, so this is the pixel at where I want to compute the value, so this has to be -1 and this has to be 1. So already you could sense something here. This is not symmetric as such. Can you quickly tell me which among these masks are symmetric? Obviously this one is symmetric. So that's a 3 by 3 mask I am going to use there. And this is, assume that this is my 0, this is my origin. So that's f of x where it is 0. And let me take out 1 by 2 out, and these two f of x plus 1. Okay, so this is 1 and this is -1. So this is a symmetric mask. So usually we prefer symmetric mask for convenience. So that's how, so that you don't even have to then mention where your origin is also there. So this is the mask you have, isn't it? So in case of a 2D image, of course now it will become 3 by 3 mask. Okay, this is a non-symmetric mask that we have written earlier itself. Okay, this of course 1 by 2 is taken within this. So that's as far as the gradient in the x direction is concerned. In similar lines, you could write a gradient in the y direction also. Okay, so maybe I'll stop this video here and I'll continue the rest about other types of edge detectors, and then followed by the Laplacian in the next video lecture. Thank you for watching. See you in the next video lecture. Bye. Take care.